Well, hello and welcome back to the next installment of our trip down memory lane. We're going to talk about locality of reference in programs today. But before we get into that, I want to provide some context for why this is such an important concept in our computer systems. So, one of the things that is important for you as a programmer these days is that you have to have some understanding of how the multiple cores in our machines work and what kind of ramifications there are for ensuring that our programs are efficient and effective. So, over the years, we've talked a lot about how cycles measure memory access and instruction time. So our computers have what's called a clock cycle. Now, in order to understand this and recognize how fast our machines actually run, I want to remind you that a nanosecond is 10 to the minus ninth seconds, and a microsecond is 10 to the minus 6 seconds. And we typically measure our CPUs in terms of what's called a clock cycle. This is how many times per second the CPU is ticking over its clock. Now, sometimes that means that's how many times it's executing an instruction, but that's not always the case. Some instructions might take more than one clock cycle, so this varies per instruction. But a CPU could typically operate these days at around 2 gigahertz, which is 2 million hertz, or 2 million cycles per second. And in that case, one cycle then takes 1 over our that number, or 5 times 10 to the minus 10th seconds, 0.5 nanoseconds for one clock cycle. And so our instruction cycle now is different. That is the time to fetch an instruction from memory, have the CPU decode it, and then execute it inside of the arithmetic logic unit. Now, this might, for some instructions, take one clock cycle, like I said, but sometimes it doesn't. And so we sometimes use this measurement cycles per instruction. So the number of clock cycles needed to complete a particular instruction, that's measured as this ratio. So it might take 5 clock cycles for a very complicated instruction, might take 1.5. But then some instructions are even less than or equal to 1 clock cycle per instruction. So it does vary by instruction. So we don't use this term cycles per instruction as often when looking at the specifications for a CPU, because it can vary per instruction. So often the number that's always reported is this clock cycle. How many gigahertz is a particular CPU running at? And so here is a table showing that measurement over history from 1985 to 2015. And I'm going to talk about even past 2015 in a moment. But one thing to notice is that over time, this clock cycle kept improving. So you see here how this clock rate, and therefore the cycle time itself, kept increasing. And then in the early 2000s with the Pentium 4, Intel ran into a lot of trouble trying to go past this 3300 number. And even at this 3300 number, this Pentium 4 processor needed a massive heat sink to try to dissipate the heat that was being created by running this fast. And so this time period is typically called the power wall. It took more power to run a CPU at this speed, and that power therefore generated more heat. And so this became untenable. You could no longer have a laptop running at speeds like this because it would just get too hot. You couldn't have it sitting on your lap or even on your desk. And so Intel in the early 2000s sounded the alarm and said, look, people, we're going to start making multiple cores. We're going to run them at a little bit lower clock cycle here, but we're going to have two of them. And so you're going to have to use 2 in your code, or 4 as time went on. And typically now we have 4 cores in a lot of our processors. This is increasing. I'm going to talk a little bit about that in a minute. Now, one thing to notice about that is that they started out dropping the clock rate. Now, it has since crept back up again, so they are able to run it faster at lower power. They figured some ways to get around this. But generally speaking, what's happened is that the cycle time for a Pentium 4 here was 0.3 nanoseconds. But then when we start having more than one core, even when we drop the cycle time because the clock rate goes down, we still can have an effective cycle time that's less because we basically take this cycle time and divide it by the number of cores we have, and that's effectively how fast our machine can be going if we can take advantage of running something on both of those cores. And that's the part that has ramifications for you now, because we really have to take advantage of these multiple cores and this effective cycle time by knowing how to program our computers to take advantage of that. And so what you see interestingly here is how this effective time is going down. And by 2015, they were able to increase the clock cycle a little bit and still make that effective time go down. And then this last column, or this effective cycle time, the cycle time over the number of cores is now decreasing here. And then this last column, you can see the overall increase over time. And what's really dramatic is how much this effective cycle time is increasing as we add more cores to our machine. And what's really interesting now, for quite a few years here, 4 was sort of what we would have in our laptops. And but this is changing now. And in higher end laptops these days, there's now a core, what's called an i9. And this is available in, say, your MacBook Pros. And it's still approximately the 3 gigahertz number here, 3000 megahertz. But now we have 8 cores. And so you divide this effective time in half again. And this effective cycle time is going down again. And so that's pretty interesting. We have a lot of power to run instructions if we can write programs that'll let us do that. And it certainly lets our machines run more things simultaneously as well, different programs. So this increase since 1985 is really amazing. It's 4,000-fold from even 2015 to now. We've doubled it again. This increase in effective cycle time. And we're not going to just go to 16 anytime soon, but we see this trend going on. So in the dawn of time back here, when we had single processors, things looked kind of like this. And we had only 2 levels of cache, along with main memory for our single CPU. And I'm going to talk about what the D and I are later on. So then these days we have at least 4 cores. And now, as I was saying, even sometimes 8. And the difference here is that another level of cache has been added that gets shared by all of the cores. And we're going to be talking a lot about these levels of cache and how things work going forward. And then we still have our main memory down here. So each of these cores now has their own registers as well, and therefore can be executing different programs or parts of a single program that's been parallelized. So now, historically then, what we are seeing is an interesting picture like this. So in the last presentation, I talked about different types of memory in the hierarchy, disk up here being the slowest. So here is access time for various types of hardware from our disk and then down to our CPU. And so hard disk slowest in the memory hierarchy. The SSD flash drives are in this range. Their access speed is not changing very much since 2015. You can see the hard drive went down, but then now has just, completely flattened out. Here's our main memory. This is still getting a little better, but there will be a time at which this pretty much flattens out as well. SRAM is the static RAM that's used for cache. That's faster yet, but you see it too is not changing that much anymore in terms of access time. But what we saw from the previous table is that this effective cycle time for a CPU is faster. So the CPU is still running faster than any of these times that we can access any of the memory on the machine. And so we have what's called this gap here between what the original cycle time was and now what the effective CPU cycle time is, because we have gone from 2 to 4 CPU cores in our CPU, and then here due to the increase in the speed itself of each of those 4 cores. And then, of course, what's happening now is now in 2020 with one of these 8-core machines, this gap is just widening even further. And it's further away from, say, our disk, our SSD, our DRAM, and our SRAM access times. And so this could be a problem. The CPU could be sitting here waiting to do things because it's waiting to read either from SRAM or DRAM, and heaven forbid disk when your program is first starting up or when you're accessing a large file that's on disk. And so this could be a big problem. Basically, we might not be using all these effective cycles very effectively at all. And so even back in these days when there was this gap, the designers of the machines discovered something about programs that really helps us here to still be able to let the CPU work as fast as it can. And so this is called locality. So it's the key to bridging this gap between CPU and the various levels of memory. And it's a property of our programs themselves. So let's examine this. So the principle of locality goes like this. Programs tend to use data and instructions with addresses near or equal to those they have used recently. So remember, our program and our data are stored in our memory when the program loads up. And so one type of locality is temporal locality. So recently referenced items are likely to be referenced again in the near future. So part of our data is likely to be referenced from memory more than once. This is called temporal locality. So near each other in time, data is being accessed in memory. There's also something called spatial locality. So items with nearby addresses in memory tend to be referenced close together in time. And we'll see some examples of this kind of thing with a solid example here. So here is a small bit of code where the elements of an array are being summed up together. And remember, our array now is going to be stored over here in memory along with the code for this small code example, the actual instructions that are going to get executed. So when we have certain kinds of data references, such as accessing the read-write data, or maybe it's read-only data, either way, so the data that's stored in memory for our program, we might do something like reference elements in the array in succession. And that's exactly what's happening here. So we've got our array A, and we're starting at A0, and we're incrementing the index here and accessing every element in the array. We call this a stride 1 reference pattern because we're going successively one element in the array after the other. And this kind of example is spatial locality. We are spatially looking at one set of bytes in memory after another, because we know this array is stored contiguously in memory. So as we access each element, we are accessing something next to the previous element. And then another interesting aspect here about the data references is the variable called sum. Now that's referenced each iteration of that for loop up here. So each time through the for loop, sum is being referenced and updated. That's called temporal locality because the instruction here is being executed over and over again in time. So this data is being accessed over and over again in time. We also, just for the set of instructions that would make up this small bit of code, we reference those instructions in sequence. We've seen what our assembly programs look like, and they get executed one after the other. That's the nature of the way our programs work, right? And so we reference each of those instructions, the code itself, in sequence. And so that is an example of spatial locality. Our programs in general have reasonable spatial locality. Now, there's also a set of instructions for this loop that get executed over and over again, and as we cycle through that loop. So there's also some temporal locality where over time the same set of instructions get executed over and over again. And so just this very simple little program has examples of spatial and temporal locality for both the code, the instructions, and the data that those instructions are operating on. So one interesting thing to ask yourself is, well, besides sum, what other data exhibit some sort of temporal locality here? And I'll let you think a little bit about that before I jump right in and say what it is. Look at that code and try to think about that. What else exhibits some temporal locality? Hopefully, after looking at it, you've figured out that it's I. I keeps getting incremented over and over again. So temporally, we are accessing I and updating it many, many times in succession. So there are some C statements that don't necessarily have temporal locality in this example. We've sort of run out of most of them. It's really this one up here. When we initialize sum to 0, then we never execute that again. And in fact, we also only execute this return one time, right? So there's a couple of statements that don't have a lot of temporal locality. They're executed once and then never returned to again. So one thing that we can do is we can look at a program, and I will claim that this is a skill every good professional programmer must have, is to be able to look at some code and get a qualitative sense of its locality, because it's really important to make sure that you're taking advantage of the locality, and we'll see why as we dive further into this in the next few presentations. But so here, the most important way this comes through is with 2D arrays. So you remember we studied how C stores our 2D arrays in this row major ordering. So the first row of a 2D array is stored first, and then the next row, and so on. You remember this picture. And when we declare our arrays, we declare the row and the column like this. And so here's our first row, going from A00 to A0 n minus 1, for example. So, so this method of storage of our array has a direct influence on the locality of our programs. So let's look at this program here that is using this array A now. And the question we want to pose to ourselves when we look at a piece of code like this is, does this function have good locality with respect to array A? And I would even go further to say, well, let's look at the spatial locality with respect to this array. And you see here that we are executing some code similar to the one-dimensional array, but now in 2 dimensions. But so what is happening here? This inner loop is updating I. And so each time through, I goes from 0 to 1 to 2, right? And you might get a hint from the name of this. This is called sum array columns. Well, that's because this really is going through in column order. And so each column is being updated as we go through this inner loop. One of these arrows matches the one pass of the inner loop, right? So what's interesting about this is that that is a stride n reference pattern. We're skipping all n of these and going down to this one as we go through the first column. And with 2D arrays, as you can imagine, a stride n reference pattern is pretty bad. And that gives us poor spatial locality because basically we're accessing this element and then this one and then this one and then each of the first ones till we get down to here. So we're skipping a whole bunch in between every time. And that gives us poor spatial locality of reference. Now let's look at this example code, which we conveniently call sum array rows, where we have switched the loops now. And so the inner loop, the J is being updated. And so that means we are, in fact, looking at rows instead. So if we want to think about the spatial locality of this, we are going down row by row, right? And so this, in this particular case now, is what we call a stride 1 reference pattern, because we're going to go one at a time through memory, how it is stored on our machine. And so, of course, you can get a sense now that a stride 1 reference pattern gives us good spatial locality of reference. And so this is the thing that you want to be able to do when you look at code, is to have a qualitative sense of that. Later on, we're actually going to quantify it as well. But to start with, we want to at least have a qualitative sense of this. So now let's kind of sum this up a little bit. So we've seen how we've got this memory hierarchy, and it has been organized in this way such that the lower, cheaper, slower memory is at the bottom, and we do see this widening in this gap, so we have to be aware of it and figure out how we can take advantage of it. But if we write good programs that exhibit good locality, this is going to help us. So these properties actually complement each other very well. And so we are going to use the memory hierarchy to cache some of our data at these higher levels. And I'm going to go through an example of that with you now. So the system works well using this hierarchy if we have good spatial and temporal locality, and both for data and for the instructions. And so let's have a look at this example sum array rows. We had decided that in general this has good spatial locality. This is the C code. This is the corresponding assembly code. So this is the set of instructions for this code. And this is that loop going on. So this is where we tend to have that temporal locality. And we knew that the data from some array rows was exhibiting good spatial locality because of the stride 1 reference. With the code here now, the instructions themselves have some temporal locality by the nature of this loop. And then just in general, because of executing one instruction after another here, and then looping around and executing one instruction after another, our programs will typically have pretty good spatial locality, especially some small function like this. But if you do have a function that tends to, a program that tends to call a lot of different functions back and forth, you might not have always really good spatial and temporal locality in your program. So it is something to think about. This particular example has good both spatial and temporal locality because of the nature of how this little function is running. So now what happens when we are running our program then is it starts out by setting aside a spot for this array in our main memory at this level of the program. So it pulls it from our either a solid state drive or a spinning drive and pulls the program up and also puts that into main memory. So we've got both our instructions and our data now in main memory when the program starts running. And now as the program is beginning to run, what happens is what's called the instruction cache gets populated, and it really gets moved all the way from level 3 up to level 1 straight away. For example, the part that's running the loop over and over again will probably stay in the instruction cache portion of level 1 cache. And then as we're looping through that array, what's happening is that a block of that array, part of that array, is going to be moved into cache. It'll start at level 3, but it'll immediately move up to level 1. And then as the program is looping through, when our data is in cache, it's able to access it here. And this is how we take advantage of the hierarchy. We read in not just one element, but a portion of the array. I happen to have shown a row of the array being read in. That isn't always the case. It might, if the arrays, if the rows are really big, it might only be part of a row that gets moved in. But the idea is that part of the array is going to get moved into cache, and then as the program's executing, we're able to access some of the elements of the array at a much faster speed because it's been moved up into level 1 cache. So as soon as we access 0, 0, we actually move more than 0, 0 into cache. And that is the way that the caching system works. And then so as we get to the next row, we're going to have to read that from main memory, and it's going to move up into the other portions of cache. And then we're going to be able to read through that much way up here in level 1, so it'll be faster to access it. So this is the way that our system is able to take advantage of the cache. And, as we keep going, we would read more and more. It might be that the whole array doesn't necessarily fit in cache. That often happens. And so at some point, we might read one row and it'll end up back in cache over here where the 0th row was. But we'll see this kind of thing and talk about it more. But this is the general conceptual idea of program caching, is that we're going to cache both our instructions and our data. So you remember one core has cache inside of it. And so part of it is for instructions. And so that's the L1 instruction cache would hold these instructions for looping through our array, for example. And then there's also this data cache, which is where the elements of the array would get stored. And so this is the general idea. And what you're going to now do in memory activity 1 is to use the running time of your program to see whether or not something, what the effects of poor locality actually are. So you'll be able to see that a file or a program runs, excuse me, slower if it has poor locality than if it has good locality. And so this is just fascinating. This is empirically, we could actually see this happening by taking some data. And so that's these memory activities are all about that, getting some empirical evidence for conceptually why it is that having good locality makes our programs more effective. So go ahead and try memory activity 1 now.